This is Unit 2, Topic H. We're going to learn in this section about a chain rule for derivatives. The chain rule is a method that we use to find the derivative of a composition of functions. So if I've got the composition f of g of x, and I want to take its derivative, there's the prime. The derivative is f prime of g of x times g prime of x. So notice what we've got here. We've got the derivative of the outer function times the derivative of the inner function. So that's the way I usually think of the chain rule. Derivative of the outer function times the derivative of the inner function of the composition. Again, I haven't really proven this rule to you, so let's start with a problem that we could do two ways. Once using what we already know, and then again using the chain rule. So using what we know so far, if we wanted to take the derivative of 4x plus 3 squared, we would have had to have multiplied this out. 16x squared plus 12x and 12x would be 24x. Plus 9. And then y prime, pretty simple, right? Just 32x plus 24. Let's redo that same problem now using the chain rule. In order to use the chain rule, we need to identify what we mean by an outer function and an inner function. The outer function of this composition is the squaring function. The inner function is just the 4x plus 3. So to do y prime, I'm going to start by taking the derivative of the squaring function. That's just going to be a power rule, right? I'll bring the 2 down in front of all of this and decrease that exponent to 1. And then I have to multiply by the derivative of the inner function. Well, the derivative of that inner function is just 4. So I end up with 4 times 2, or 8, times 4x plus 3, and there's that 32x plus 24 again. So the good news is, looks like everything works out, right? We got the same answers we would have gotten even without the chain rule. And so the next question, kind of like with our product and quotient rules, is since it was probably easier to do this way, by multiplying first, is there any real reason to even have a chain rule? And I think you'll recognize the answer to that question very quickly when we look at problem 2. Is it doable to multiply this out first before taking the derivative? It's doable, but it's not a lot of fun, right? To raise that to the 7th power would take a lot of work. So much easier this time to just go straight to the chain rule. dy dx. First I take the derivative of the outer function, the power rule. So 7 times all of this to the 6th power, which is my normal power rule. And then I have to multiply by the derivative of what's inside. The derivative of this would be negative 3. So I'm going to get negative 21 times negative 3x plus 5 to the 6th. And that's going to be the simplest way to leave that answer. All right, let's try a few more. In number 3, if I'd like to take y prime, the outer function would be the cotangent function. The derivative of the cotangent function is negative cosecant squared. The argument will not change. It's still x squared minus 4x plus 5. That's what I was taking the cotangent of. That is therefore now what I'm taking the cosecant of. So there was the outer function's derivative. I now multiply by the derivative of the inner function, 2x minus 4. Not a whole lot I can do here. Probably just going to bring the negative into the multiplier. So maybe I'll call that negative 2x plus 4 multiplied by the cosecant squared of x squared minus 4x plus 5. When you're doing derivatives that include trig functions, unless you've used a trig identity somewhere, the argument of the trig functions will remain consistent all the way through the problem. So this was the argument in the original function. It's still the argument in the derivative function. So using that same idea, take a look at number 4. My outer function this time is the cosine function. So the derivative of the outer would be negative sine of x to the 5th. Again, notice I'm not changing the argument of the trig function. Times the derivative of the inner function, 5x to the 4th. Again, not a whole lot to be done. I'm just going to bring that negative 5x to the 4th to the front and call it good. All right, take a good look at the difference between number 4 and number 5. Here, the x to the 5th was inside. It's what was done first, right? And the cosine was the outer function. Here, we're actually doing the cosine of x first and then raising the result to the 5th power. I really recommend rewriting this as cosine x raised up to the 5th power because it makes it much easier to see how the chain rule is going to work. Oops, you know what? Up here, I forgot to label my derivative. That was bad notation. Go back and do that. All right, taking the derivative here. The outer function is actually that 5th power. So I start by taking the derivative of the outer function, my power rule, 5 times cosine x raised to the 4th power. I'm then going to multiply by the derivative of the inner function. Derivative of cosine x would be negative sine x. So I have negative 5 sine x cosine to the 4th x. All right, number 6, secant of e to the t. Secant is definitely my outer function, so I'm going to differentiate that first. And remember that the derivative of the secant function is secant times tangent. Both the secant and tangent in the derivative will retain the same argument. That e to the t is not going to change here. So I'll have secant e to the t, tangent of e to the t. Then I have to multiply by the derivative of the inner function, and the derivative of e to the t is e to the t. I'll bring that last factor of e to the t out front and rewrite my derivative one more time. All right, let's try one more like that. In number 7, the exponential, the e, is really the outer function. The t squared minus 4t would have been done first. That's the inner function. So when I go to do my derivative, dw dt, I'm going to start with the derivative of the outer function. The derivative of the exponential base e is itself. So I'm still going to have e to the t squared minus 4t. Then I have to multiply by the derivative of the inner function, 2t minus 4. And other than writing that 2t minus 4 in front, that's done. All right. Sometimes we have to use a combination of derivative rules to get our final result. So we now have product rules, quotient rules, and then now our new chain rule. And in each of these next few examples, we'll use 2 or more of those to find the final derivative. So take a look at example 1. Do you see a product here? We would have f is x cubed, and g is e to the 5x. So f prime, 3x squared, and now g prime. Notice we're going to have a little chain rule here. The derivative of the outer function is still e to the 5x, but I've got this inner function, 5x, so I have to multiply by the derivative of that, which is 5. And then overall, I'm going to do my product rule, fg prime plus gf prime. So little f prime of x, fg prime, we'd have 5x cubed e to the 5x plus gf prime, right here, 3x squared e to the 5x. And although you could factor that or something if you wanted to, there's no reason we have to. That's a perfectly good simplified form. All right, what about number 2? There's that power of a trig function again. Let's start by rewriting this. That would be the sine of x cubed, all raised to that 6th power. What I actually have here is a double composition, or in other words, I'll need a double chain rule. The outermost function is the 6th power, and then the sine function, and finally the x cubed. So we're going to use a double chain rule on this. I start with the outermost function. The derivative there is just a power rule. 6 times the sine of x cubed raised to the 5th power. I now go to my inner function and take its derivative. The derivative of sine x cubed would be cosine x cubed. But there's yet another inner function. The derivative of x cubed is 3x squared. And you might perhaps be starting to see why the chain rule, or where it gets its name. You have this sort of a chaining action as you sort of keep on pulling out derivatives as there are deeper and deeper layers of inner functions. All right. The only thing I can really do to simplify this would be to multiply these together. So 18x squared, sine to the 5th of x cubed, cosine of x cubed. All right, let's do a couple more combinations. In number 3, I definitely see a quotient there. F would be the top, which I'm going to choose to write as 3x plus 2 to the 1/2 power. I know fractional exponents make derivatives easier to work with. G is the bottom, 2x minus 5. So for f prime, I'm going to use a power rule. My outer function is a power. 1/2 times 3x plus 2 to the negative 1/2 times the derivative of this inner function, which would be 3. So I have 3/2 times 3x plus 2 to the negative 1/2. Thank goodness G prime is simple, right? G prime is just 2. All right, so quotient rule, we're going to have GF prime minus FG prime over G squared. So our derivative dy dx, GF prime, 2x minus 5 times 3/2 3x plus 2 to the negative 1/2. Minus, I should have given myself more space here, FG prime. FG prime is just going to be 2 times 3x plus 2 to the 1/2. Over G squared, 2x minus 5 squared. All right, there's not, depending on how much you want to do with this, there's more and less we can do to simplify this. Let's go ahead and kind of take a look at how simple this can get if we do a little bit of algebra with it. This negative 1/2 is really a square root in the denominator, right? So let me rewrite this as 3 times 2x minus 5 over 2 times the square root of 3x plus 2 minus 2 times the square root of 3x plus 2 all over 2x minus 5 squared. I would like to clear out this complex fraction, so I'm going to multiply the top and the bottom by 2 times that radical. Let's see if I can sneak this in without encroaching on the next problem too much. So I'm going to get, let's see here, that'll give me a 6, no, excuse me, I'm going to let the 2's cancel, aren't I? So here the 2's will cancel and the square roots will cancel. Those are just gone. So I'll have 6x minus 15. Minus, here we go, 2 times 2 is 4. And when you multiply the square roots together, you get 3x plus 2. So that was pretty nice. All the radicals completely canceled out on top. In the denominator, we've got 2x minus 5 squared, square root 3x plus 2. So what have I really got up here? 6x minus 15 minus 12x minus 8 would give me negative 6x minus 23 over that whole denominator. So it is a little bit of algebra, but it gives us a relatively simple result. In particular, notice how nice and simple my numerator gets here. As we'll see later on, that's going to have some advantages when we start using these derivatives in some other kinds of problems. All right, how about number 4? My outer function is the cosecant function. I know how to take the derivative of that. And then I'm going to notice my inner function is actually going to be a product here. So let's start f prime of t by saying the derivative of cosecant is negative cosecant times cotangent. And remember, the arguments of the trig functions stay the same. So this t squared e to the 3t is the argument of both the cosecant and the cotangent. Now I'm going to have to multiply this by a product rule, right? The product rule that represents the derivative of this inner function. So f would be t squared, and g would be e to the 3t, giving me an f prime of 2t, and a g prime of still e to the 3t. Exponential base e is its own derivative, but then because of the chain rule, I'd have a times 3 on that. It's product rule, fg prime plus gf prime. So this product rule, fg prime, would be 3t squared e to the 3t. Plus gf prime, 2t e to the 3t. And there's not a whole lot that I can really do with that. This negative could probably just get distributed through here. So I might have negative 3t squared e to the 3t minus 2t e to the 3t times the cosecant and the cotangent. And it's not beautiful, but there it is. There's our whole derivative. All right, number 5. We have e to the cosine of 4x. I'm seeing another double chain rule here. My outer function is the exponential base e. My next inner function would be the cosine function, and then finally the 4x. So let's see what we can do. dy dx. First of all, the derivative of the exponential is going to be itself, e to the cosine 4x, times the derivative of this 4x, or excuse me, of this cosine 4x, would be negative sine 4x. And then one more chain rule, we still have 4x as an inner function, and the derivative of the 4x would be 4. So I could pull the negative 4 out in front, and then I'd have e, well actually let me put that sign, well it doesn't really matter, e to the cosine 4x times the sine of 4x. All right, one more example of a combination rule problem. Number 6 here. I've got this cubed root, and as is really common, we may want to rewrite that as x plus 1 over x minus 5 to the 1/3 power, right? Easier to work with fractional exponents. So I'm seeing the 1/3 power as my outer function. I'll be doing a power rule first. But when I get to the inner function, it looks like I'm going to need a chain rule. Or excuse me, a quotient rule. So I would have w prime is 1/3 times the x plus 1 over x minus 5 to the negative 2/3. There's the power rule part. Times the derivative of the inner function, which is going to take a quotient rule. So f is x plus 1, and g is x minus 5. F prime would be 1, And G prime would be 1. And then I'll just go with GF prime minus FG prime over G squared. So let's see, GF prime. X minus 5 times 1 is just x minus 5. Subtract FG prime. X plus 1 times 1 is just x plus 1. And the denominator, the G squared, would be the x minus 5 squared. All right, as we write this all out, let's see if we can do a little bit of simplifying. I'm going to go ahead, and I notice I've got some x minus 5s in 2 different places. It would be nice if I could eventually combine those. So as I start to write this out, I'm going to say a multiplier of 1 on top. I don't need to worry about that. But then I'd have an x plus 1 to the negative 2/3. And on the bottom, I've got a 3 and an x minus 5 to the negative 2/3. So that's just this first piece. I've just sort of redistributed how I've written it. Up here, I can see that x minus x is going to be 0. And then I'll have negative 5 minus 1, so negative 6. And on the bottom, I've got x minus 5 squared. Great. So let's keep going a little bit here. I've got the negative 6 divided by 3, so that's negative 2. And then I've got the x plus 1 to the negative 2/3. And on the bottom, since these are the same factor, I can just add the powers. 2 minus 2/3 would be 4/3. Nothing really wrong with that, but I've gone this far. Let's go to the last step. I had negative exponent. I could just move that to the bottom if I wanted to. So I could make that x plus 1 to the 2/3 in the denominator, and then x minus 5 to the 4/3. And that would be a pretty nice, simple form of writing our answer. All right, so there's a bunch of examples of using the chain rule, even in combination with the other rules that we've already learned. In the next video, we'll take a look at some application problems that require the use of the chain rule.